Sine says. The law of sine says that if you have a triangle, then there's a relationship between the sides and angles opposite, and that relationship is summarized by this. You take the sine of an angle and divide by the side length opposite. It's the same no matter which pair you pick. And this is useful because you can use it to determine lots of things about the triangle. If you know all three angles and you know one side length, well, you can just use the law of sines to determine the other two. If you know, so here's like the weird situation that we spent the last half hour of last time on. If you're in a situation where you know A, you know B, and you know this angle little a, you have a side-side angle triangle, then you have enough information to totally determine everything about this triangle. Ish. There's maybe an ambiguity. And let's just talk through this flowchart. We'll see how it should walk. In looking at this triangle, is there a pair consisting of a side and an angle opposite, both of which you know? Yeah, it's the A's, I guess. You know these two. Is there a pair consisting of an angle and a side opposite that you know one of, but not the other? Nice. It is possible then to use the law of sines to determine B. And let's write down how to do that. So, that's the first bullet point, second bullet point, third bullet point. You write down the law of sines equation, you get this. And you'd like to solve that for little b, start by solving for sine of little b. You'll get b sine A over A. That seem about right? And there's not a point in memorizing what I just wrote in that blank, right? Because what I wrote in that blank is just divide both sides by b. Multiply both sides by b. So now you should ask yourself the following questions. Take this thing, in any given application, you'll know what big B, big A, and little a are. You can get a decimal approximation for this. Ask yourself, is that thing bigger than 1? And that's important because what's the biggest that sine of B can ever be? 1. So if this says that sine of B is bigger than 1, you're done. There are no solutions. You should stop. Otherwise, there's at least one solution, and you can find that solution. It's inverse sine of this thing in green, b sine A over A. But again, don't just memorize what goes in that blank. You're just taking the inverse sine of both sides of this equation, right? And here's the neat trick. If this side length big B is not the longest side in the triangle, then the angle little b must be acute. There's the acute angle that has that sign. So in the case that little b has to be acute, there's only one solution. There it is. If little b might be obtuse, so that would be the case if big B is bigger than big A, because then big B might be the longest side. Because you don't know the side length of big C, so you can't compare it. If big B is bigger than big A, then the angle little b might be obtuse. Inverse sine will never find an obtuse angle. Inverse sine only ever returns acute angles. So if the angle might be obtuse, you have to manually force it to be. So the two options are sine inverse of that stuff, or the obtuse option. How did you get the obtuse option once you knew the acute one? Yeah, you definitely do one or the other. Maybe flip back some previous pages for some examples. Pi minus the acute option. Or if you want to walk in degrees, because sometimes you do want to walk in degrees, 180 degrees minus the acute option. Neato, that seemed pretty good. And so now you know the angle little b. You know two angles now. That means you know the thought, because angles have to add up to 180 degrees of pi radians. There's still one side length missing. Use the law of sines to find that. Is that a decent summary of what we did yesterday? Nice. So now we have this flowchart. Let's apply that flowchart to these examples. And I'm not looking for like a conclusion of here is the solution. I just want the conclusion of how many solutions are there. Is it 0, 1, or 2? And what do people think? Is it clear how to use this flowchart to answer those questions? Anyone want me to talk through one before I have you do the other two? Cool. I'll do the middle one just because it's in the middle. So let's see what happens. So here's a triangle problem. Am I told what one side length and one angle? Does this fit the setup at the top of the page? Nice. Then let's use that flowchart. Locate a known angle and known side opposite. Those two I know. I don't know b, but I do know the side length 3. So I can write down something using the law of sines. Sine of b over 3 is equal to the sine of 10 degrees over 1. You couldn't see what I wrote? But I said it. Nice. In the step-by-step summary above, the next thing it says to do is solve for sine of b. What do you get when you solve that for sine of b? Nice. So there is the exact value, but I'm actually more interested in the decimal approximation this time. What did you say it was? Like it was 1 point. Like that? 31. Wait, 31.3. That's way too big. I don't believe that. Say louder. I hear a 0.52. So let's see where we disagree. Did I screw up that bit of algebra in solving for sine of b?
No, I already solved it.
Oh, you went all the way to determining the angle. Yeah, I don't want to go that far. You did something that you would have to do if I wanted you to actually solve the triangle. So that's great. So let's ask ourselves this question next. This angle b, oh, well, that is not bigger than 1, so that's good. So that line does not say sine of b is bigger than 1. So it is not the case that there are no solutions. There will be at least one solution. The side length opposite the angle little b, is it possible that that side length might be the longest side length? Three is bigger than 1. So the angle b might be obtuse. It doesn't have to be obtuse, though. It might be acute. So you already told me one of the choices for b. You told me b is like 31 point something. Cool. That's good enough for me. So there's the acute option. And let's also get the obtuse option, even though I said that I don't really care about the obtuse option, like the actual numbers. How do you get the obtuse option? Yeah, subtract it from 180. So what do you get when you subtract that from 180? Cool. I guess with the decimal the decimals that I skipped. You said 138-ish degrees? Cool. So there are two different choices for the angle little b. So how many solutions are there to this triangle problem? 2 solutions. And in fact, I could have made that conclusion there. I didn't actually need to find the angle little b. That idea seem sensible? All right. So let's think about the remaining 2. So I think I want everyone to do each of those 2 examples. But which one you do first, you can pick. And maybe like, if you want to compare your walk with those around you, maybe coordinate which one you want to do first. So I'm not asking for like what the angles are or anything. I just want the answer of how many solutions are there. 0, 1, or 2. People feel okay about coming together on this? Yeah, and let's start by jumping right to the conclusion, then we'll decide if conversation is needed. First example, no solutions, one solution, or two solutions. No solutions, one solution, two solutions. Cool, that seems pretty unanimous. All right, so tell me why. Why no solutions? Yeah. Nice. So when you try to find angle B, you find that it, meaning sine of B, was equal to something, and that something was bigger than 1. Cool. That agree with the summary that most people did? Do people want more discussion than that? Groovy. How about that last one? No solutions, one solution, or two solutions? None? One? Two? I think I agree. And in fact, it better be that, otherwise, like, why are there 3 examples and 3 options if one option gets used twice? That's like a trick you do on homework, not in class. Call for discussion? Yeah, let's discuss. So, let's go through the process of like what you wound up doing. So step 1 was like you solve for the sine of B. And I'm going to put some ellipses there because there's an algebra that got skipped. What did you wind up getting for sine of B? 0.057. Does that agree with someone else? Okay, nice. Is that bigger than 1? All right, so that means that there will be at least one solution. Because of this, there will be at least one solution. And the only way to get to 2 solutions is if the angle B might be obtuse. So let's take a look at this triangle. The side opposite B, is it possible for that side to be the longest side in this triangle? Because it's less than the side length 3. 1 is less than 3. So side opposite B can't be longest, so B can't be obtuse. Let's put some apostrophes in those contractions, Chris. So since it can't be acute, obtuse, it has to be acute. Since it has to be acute, it's the angle that inverse sine will give you.
Could you quick track back to the first one we did and how we got B equals 148 degrees?
This first one? Yeah. Yeah.
I'm trying to do follow up on the math here, and I just got I'm not getting
Yeah.
158. I'm getting like 148.
I am low on space. In fact, 148. Maybe I think I'm getting 148 too. Let's use a machine. So, this situation says that sine of B is 3 times sine of 10 degrees, or about 0.52. So if I want to get the acute choice for B, I'll take the inverse sine of the right-hand side of this equation. If you want to be approximate, use 0.52. There will be some rounding error. If you want to be exact, use the thing above. 3 times sine of 10 degrees. So let's compute the arc sine of 3 times the sine of 10 degrees. Make sure you're on degree mode. I get 31.39. So far, so good?
So far, so good.
All right. So now, if I want that if I want the obtuse option, I need 180 degrees minus that. And you can do this on your calculator easier than I can with the tools I have. Because, well, that's not 180. So inverse sine will put it into radians. Since I'm using Wolfram alpha, I need to manually convert 2 degrees, then subtract it from 180. I get 148.6. So I agree with the 4.
Okay.
But that wasn't the point of this exercise anyway. There are 2 solutions. Groovy. Is it clear, like, I'll give you a second to double check yours. Are you getting the same? Neato. So here's why I know that the 138 shouldn't be right. These 2 options should add up to 180 degrees. Because right, one of them is 180 degrees minus the other. And there's rounding error, so it won't be exact. But a 10-degree error is too big for the approximations to the precision that we have them. All right, right now, if we add those together, we get like 179 degrees. Cool. I suspect a weird calculator error. We can talk about it right after class if you want to. Cool. So we're feeling pretty good about law of sines? Nice. Then I will advertise. Here's an extra credit immediately after the section in the notes. Figure out why the area formula and the law of sines are true. Neither of them are like true for like deep or difficult reasons. They're just not the focus of the class, so that's why they're relegated to extra credit. Go through these 2 pages. If you want to come talk to me about things just with some progress, that's fine. Get some extra credit for it. Finally, this tool, the law of sines, is what software is actually used when they determine the heights of things. Borrow from me this angle measuring tool. Or I guess if you have an app in your phone that measures an angle of elevation, use that. Grab also from me a tape measure. Figure out the height of a building on campus. Cool. Now, let's start in on the last tool we need to solve triangle problems. Let's talk about the law of cosines. And in order to motivate the law of cosines, like why we need another rule in addition to the law of sines, let's look at this triangle at the bottom. So let's suppose I wanted you to solve that triangle problem, and you can just find the side length C. This problem is like really resistant to an attack using the law of sines. Because the first thing the law of sines asks is there an angle and a side opposite, both of which you know? Does this have an angle and a side opposite, both of which you know? So that's annoying, because then if you write down any of the law of sines equations, you get like 2 unknowns instead of 1 unknown. That doesn't make it impossible to use, it just makes it annoying. So, instead, we'll get a new tool, and here's the motivation for that new tool. So the law of sines is like the analog of SOHCAHTOA to non-right triangles. The law of cosines is like the analog of the Pythagorean theorem to non-right triangles. So let's start with a right triangle. So let's suppose you had a right triangle, side length A, side length B, side length C, right angle. What's the relationship between those sides? That's true, but like there's an equation, right? Yeah. So that C has to be the longest side because like it squares the sum of the other two squares. All right, well that's useful. But what if we let that right angle start relaxing from a right angle? So a squared plus b squared equals c squared, and then imagine the hypotenuse between my fingertips. If that angle starts getting smaller, like the distance between these 2 points gets smaller too, but there's probably still some relationship between them. The law of cosines is that relationship. And here, I'll write it down right now. So whenever you see a non-right triangle, so let A, B, and C be edges of a triangle. If theta is the edge opposite C, so I'm going to underline this in blue. If theta is the edge opposite C, then C squared equals A squared plus B squared minus, and if I just stopped right there, like that would be the law of cosine. That would be the Pythagorean identity. Pythagorean theorem. The law of cosines tells you what the error term is in it. A squared plus B squared minus 2AB cosine theta. Yeah. Oh, neat. What was it? That would do it. Yep. So you were finding the other angle in the triangle instead of the obtuse option. Yeah. So what you found, like, it was what the angle that we didn't find was in the acute choice. Cool. All right. So what are we going to do with the rest of the day? We're just going to mess around with this formula and see how to use it to solve the triangle problems that we couldn't solve already. So here is this triangle problem. That looked like you could determine the side length C using this formula? Yeah, and let's start by writing down an equation. So, let's do it. I guess maybe I'll start with this. C squared equals, and then like, you're all like writing, but tell me what to write. C squared equals 3 squared plus 5 squared, because there is side, side. Oh, that's a really bad 5. Nice. All right, so it looks like there's an equation. The only unknown is C. So it looks like the only algebra you need to do is take the square root of both sides. But I bet we can simplify the right-hand side before we take the square root. So let's simplify that right-hand side. And I guess by simplifying, you just evaluate what number is it equal to. As a comment, I don't think you need a calculator to work out that cosine value. Pi over 3 is an angle that's on your unit circle, so you should just know cosine of pi over 3. Nice. So I can replace that cosine of pi over 3 with 1/2. And you like just keep plugging away and you get a value for that. What value do you get for that? I'm disagreeing.
I just got 19.
I hear a 19. So here's the error that I suspect you're making. So you don't do 9 plus 25 minus 30 and then multiply by 1/2. That 1/2 is only multiplied by 30. And you know what, that's an excellent mistake to like see now, because on things like exams, I see this mistake happen a lot, and I'm not really sure why. That cosine of theta is only multiplied by the 2ab. So let's evaluate this. So 9 plus 25 is 34. 34. Minus 30 times 1/2 is 15. 15. Yeah, that's 19. So instead of root 2, c is in fact the square root of 19. That helpful? Yeah. So an order of operation says you resolve multiplication before addition, even if it's at the back of the equation. Oh, goody. So we've just determined the side length c. Oh, let's suppose I asked you to determine this angle that I just indicated in purple. We won't do it, but do you think you could now determine that angle? What trick would you want to use? Are you recall for law of sines? Yeah, there's one weird subtlety that can happen with the law of sines, but let's just see if it does. That angle I just indicated in purple, is it possible that that angle might be obtuse? No. It is not opposite the longest side. This angle is opposite the side length 3. That side length's 5 and that side length's root 19. It's opposite the shortest side length, in fact. So it has to be the smallest angle, so it can't be obtuse. So yeah, inverse sine will find you that. Do you think we could also use the law of cosines to find that angle? Yeah. We would wind up with an equation with cosine of theta. We could use that to do an order. All right. So let's summarize the techniques we have. Whenever you know 3 things about a triangle, like you should be able to figure out that triangle. And by 3 things, I mean like the 6 angles or the 3 angles on the 3 sides. If you know those, then you can figure out the triangle. Except if you know all 3 angles, that's not true, because you could like scale the triangle. Right? Like there's a triangle that has those angles. You can also just like increase the sides of all the legs by a factor. So all 3 angles, not enough information. If you know 2 angles and a side, well, what do? You know the 3 angles add up to 280 degrees, so you can find the missing angle. Now you can use the law of sines to find the missing side lengths. Fair enough? That sound familiar? We did that last time? If you have a side-side angle triangle, then use the flowchart on the page we were just on. Use the law of sines to find the sine of an angle. Use inverse trig to figure out what that angle is. Keep in mind that if the angle might be obtuse, there will be 2 solutions. If the equation you get out of the law of sines says that sine is bigger than 1, then there are just no solutions. If you see a side angle side triangle, then you can use the law of cosines. You don't need inverse trig to find the missing side length, like we just did. Now you can use the law of sines or the law of cosines, if you like, to find the remaining angles. And I'll give a caution on the next page when you use the law of sines. Well, I can write it on this side. If you use law of sines, make sure it's at an angle that can't be obtuse. That seemed like a decent summary of what we just did on this previous example? Yeah. The only remaining case is, let's suppose you know all 3 sides of a triangle. Does that seem like it should be enough to build the triangle? Right, like if I give you 3 pieces of wood and say put these pieces of wood together into a triangle, there's only one way to do it, right? So it's enough to figure, that's good enough to figure out everything about the triangle. So you can figure out the angles. Let's do exactly that on the next page. So let's use the law of cosines to determine all of the angles in this triangle. 6, 4, and 3 are the sides. So let's use, I think here's the procedure I want to follow. I'll go through A, and compute use the law of cosines to determine the angle A. Then I'll cut you all loose to do the remaining 2. And I'll divide you up between some of you do beta, some of you do beta. So let's do it. So let's use the law of cosines to determine the angle alpha. So I'll treat this angle like the theta in the law of cosines, which means I have to treat 4 like C. So let's use the law of cosines, which is written on the board, to do this. What do we get? So let's see. C squared, so that's 4 squared equals 3 squared plus 6 squared minus 2 times 3 times 6 times cosine of alpha. Did I write that down correctly? All right. Just by looking at that, how many unknowns are in that equation? Just 1. I bet that means we can probably solve for that one. And just like when doing the thing with the law of sines, I think we'll start by just getting cosine of alpha on its own, and then we'll think about inverse trigonometry. So let's take that, let's solve it for the cosine of alpha. And I don't know, I can do the algebra, you can do the algebra, and then we can come together. People want me to do the algebra to get cosine? Okay. Then let's do. I think I'll start by like simplifying the things that simplify. What's 4 squared? Equals 3 squared is 9 plus 2 times 3 times 6 walks out to be times cosine alpha. And I'm going to add some unnecessary parentheses. That 36 is multiplied by cosine of alpha. So I can't like say 36 minus 36 is 0 because one of those 36 has a cosine alpha next to it. All right, so now let's do some work to get cosine of alpha on its own. So I guess a good starting point is let's subtract 9 and subtract 36 to the other side. God damn it. So these like erasable pens are nice. But their lifespan's so much shorter than a normal pen. Right? You just saw me see that there are 2 pens I need to throw away right now. Anyway, so 16 minus 9 minus 36. Gosh, that's too many things. All right, there's minus 20, minus an extra 9, minus 29. I do that arithmetic correctly? Cool. Okay, so minus 29 equals minus 36 cosine alpha. I would like to get cosine of alpha on its own. So what do I see cosine of alpha equal to now? Negative 29 over negative 36. And the negatives cancel. So just 29 over 36. And now we're about to see a real advantage of the law of cosines over the law of sines. Remind me, what's the range of inverse cosine? Zero to pi, or if we want to walk in radians, 0 to 180 degrees. Any angle in a triangle is in that range. So law of inverse cosine will find me the angle. There won't be this weirdness where it'll only find the acute option. It will find the option. So if I want to know what alpha is, I can now just say alpha is cosine inverse of 29 over 36. The negatives canceled, so I threw those away. And, well, 29 over 36 isn't a number I see on my unit circle as an x value, so I can't just like write down the exact value. But I can get a decimal approximation using a machine. By which I mean you can, and you can tell me. What is that? $36.3 degrees. And let's also get it in radians. Did I hear you right? I don't know. I didn't do the calculation. I hear a second, so I believe it. Cool, so we just determined the angle alpha. There's nothing special about the angle alpha. Could we also have determined the angle beta? Yeah, because if we want to determine the angle beta, so if I want to use this as theta, there's the thing I have to use as c. C has to be the side opposite the angle that you're using in the law of cosines. Or, if you want to determine the angle gamma, you have to use 3 as the angle little c, as the angle big C in the law of cosines. So, what do you think? Do you think you would be capable of doing either one of those? I think I'll break out and have you do it. Find for me beta. Find for me gamma. Oh, where beta is the letter that looks kind of like the letter B and gamma is the one that looks like a squiggly Y. Yeah, we'll look at that. And as you do this process, if you feel stuck at any point, or even just want to like check your answer against your neighbor, do it. You can even talk to each other if you want. And you can also ask me any questions. I'll look to see if a hand goes up. previous section. If you get to a point where there's anything you want me to double check, I'll walk around. Go ahead and raise your hand if you have any questions. Yeah. Negative doesn't distribute over multiple pages. It's not very nice. So there's only
Something like that.
no, but it's so you're not using the line over 24. It's like the other one. You're allowed to write a negative 18 multiples.
Oh.
In fact, you'll notice something special about the angle as a consequence. Or you watch this. Yeah, whatever. I'm not sure if that last digit should be a 7 or an 8. It could be that there was an ending and we just say, looks like it should be an 8. Yeah, I agree. Yeah. Yeah, I agree. Do all the angles at 280 degrees? Cool. All right. People feeling good? Feel like you're coming together? Let's hear things then. So I guess I have like blanks to the right of my page. What do you wind up getting after you did some algebra and solved for cosine of beta? What fraction did you get? Cool. And I'm going to put that negative in the numerator because I'd like to simplify. That agree with other people who figured out beta? All right. So I guess that means that beta should be inverse cosine of negative 11 over 24. And what is that about? Cool. So here's the observation to make. Inverse cosine knows whether the answer should be obtuse. That angle is obtuse. If you used inverse sine to try to find that angle, how many people did try, like, renege against my instruction and try to use the inverse sine? Okay. You would have gotten the wrong answer, or would have gotten a fake ambiguity. Because you would have said, this angle might be obtuse, so there's like two options. There aren't. There's only one, only the obtuse option. Law of sines doesn't know that, law of cosines does. Feel good? All right. How about gamma? What'd you get for cosine of gamma? Yeah.
Cosine of gamma equals 43 over 48.
43 over 48. Do I hear agreement? Nice. So I guess that means gamma has to be the inverse cosine of 43 over 48. And what is that about?
26.38.
Cool. I'm going to round that to 26.4 just because I don't want to write so many digits. And let's just do a quick sanity check. We now have all the angles. Angles in a triangle have to add up to 180 degrees. Just eyeballing it, do those look like they'll add up to 180 degrees? Yeah. We're rounding everything off to the tenths. So I'll allow myself an error in the tenths place because maybe everything rounded up and the decimal approximations, which might mean that I have like an extra tenth of a degree, but it should be pretty close to 180. Cool. That go pretty all right? Nice. Did anyone on gamma decide to use the law of sines to figure out gamma? Did you get the same answer? Awesome. Gamma can't be obtuse. So you can use the law of sines to find gamma if you want. And there's no danger, because the law of sines will tell you the acute solution, and you know the solution is acute. The only danger in doing that is like when you found cosine of gamma, you like use the result of item A. So if there was something wrong in A, there would be something wrong in item C. So that's the only reason to follow the law of cosines in that case. Groovy. All right, people feeling pretty good? So, with my remaining time, of which I have 3 minutes, let's go back to applied stuff. Right, like, you could make any of these things feel very applied. You could say, well, I have the dimensions of some triangular structure I want to build. Here are the side lengths of, like, the base of the roof, and the side lengths that I have for, like, the slanty sides of the roof. Now you know the angles that you have to cut things to. Law of cosines tells them to you. Let's do 2 more that are very much like determining distances and paths. I don't think we have enough time to do both. Let's do the top one. We're walking in the woods with Robert Frost. You come to a fork in the woods. And follow the advice of Yogi Berra. When you come across a fork in the road, take it. Anyway, Robert Frost takes the path less traveled by, which makes all the difference, while you, on the other hand, take the path more well-traveled by. As a consequence of path maintenance issues, you can maintain a faster path than Robert Frost. They diverge at an angle of 45 degrees. So let's get a picture. So you're walking together, then these 2 paths diverge at 45 degrees. That looks 45 degrees-ish. There you are. There's Robert Frost. I would like to know, after 1 hour, what is the distance between the 2 of you? And like, you have all the walls in front of you, so what other things in this diagram could I fill out? With the goal being, as soon as I know 3 things in that triangle, I can figure it out. Let's hear it.
You know the distances because if you're going at a rate of 4 miles per hour and it's been 1 hour, you know that you've walked a distance of 4 miles and Robert Frost has walked a distance of 3.
Nice. That seems sensible? And like, otherwise, if instead I said you walked 45 minutes, you'd have to do some more complicated multiplication to figure out those distances. All right. Does a triangle where I know at least 3 things? So I know I can figure out the third thing somehow. And to decide how, let's start by figuring out if we should use the law of sines. Do I see a pair consisting of a side and an angle opposite that I know? Nope, so I should use the law of cosines. And in fact, the law of cosines I think will be like right easy. D squared equals 3 squared plus 4 squared minus 2 times 3 times 4 times cosine of 45 degrees. That look easy enough to solve for D? Not easy enough to solve for D in the 0 minutes I have remaining, but I could do. So, we'll come back and we'll think about this a little bit next time. Then we'll start in on the next packet. So, I'll have those packets with me next time, but if you want to grab one right now, go for it.
This one for area, I know we are just using the law of sines to find the acute and obtuse option, but how would we put that into degrees as it would walk us to in our answer?
Yeah, so we'll write down what the area formula is.
Yeah.
So again,
I have that over
I should hit the stop recording button.